Okay, thank you very much for inviting me to this event. I'm very happy to be here. This is a summary of the main points that we will touch during this presentation. I will start with a brief introduction about myself, and then we will talk a little bit about the background on Norway's EV adoption and which are the rules for Norway's leadership in this field. Then we will spend a few words on the role of informatics in the electric vehicles field. And then under the umbrella of informatics, we will talk a little bit about the key role of mathematical modeling and optimization. And then I will spend a few words about some relevant research projects where I've been involved when I was working in Norway. And then we will conclude with some discussions on the future of green transport and some concluding remarks. So just very quick about me. I'm originally from Italy. I did my master degree and PhD at the University of Bologna. Then I worked for a couple of years as a research associate in Durham in the UK. I've done a postdoc at the Norwegian University of Science and Technology, and I've been a research scientist in Sintef Energy, which is the largest research center in Scandinavia. And since 2019, I'm associate professor at the UIT, the Arctic University of Norway. And my main interest is mathematical optimization in the context of computer science with specific applications to energy and power systems. So let's have a small introduction about the Norwegian leadership in the electric vehicles adoption, so the trends and which are the rules for this leadership. So as you see from the figure, Norway shows one of the highest per capita rates of electric vehicles ownership, and it stands as a leader in the electric vehicles adoption. Here you see the total number of electric cars and vans that were registered in Norway from 2010 until 2024. And you can see that there is an exponential growth in this period, and we can notice a slight reduction in growth in the last few years, and this suggests that the market is approaching towards maturity, and we will come back to this briefly at the end of the presentation. So which are the rules for this Norwegian leadership? First of all, government policies and incentives. We have tax incentives, usage incentives, and parking and charging incentives. So in Norway, electric vehicles are exempt from the purchase taxes. They had exemption from the value-added tax. Then they have reduced or even eliminated the toll fees on roads, bridges, and tunnels. They have access to free or discounted ferry transport rates. They also have access to bus lanes so that they can reduce the travel time. And then there are free or reduced rates for parking, and also subsidies, for the installation of charging at home. So let's hear just a few words from Christina Bu from the Norwegian Electric Vehicles Association regarding these government policies.
Our politicians decided that these cars should not cost more than ICE cars, and remove the taxes. So we tax ICE cars heavily, and we don't tax these cars. To say it differently, we tax what we don't want, and we promote what we want. And this makes it possible for consumers to choose electric, and they do, and now soon the majority is doing so.
And then let's also hear a few words from Norway Managing Director.
Are Norwegians passionate about going green, or do they just like the incentives?
I think a bit of both. It is so normal now to drive an EV in Norway that if you actually buy a fossil fueled car, you need to explain yourself why on earth you would do that. Norway is a country with widespread population, high mountains, a climate with snow and ice in the winters, so not really that suitable for an EV in theory. But there we have proved the skeptics wrong. It really does work. We have been able to build out the charging infrastructure. There is charging stations about every 30 miles.
And this leads to the next important factor in Norwegian leadership in EV adoption, which is infrastructure development. So Norway has invested in this widespread charging network. So we have this extensive network of public charging stations across Norway. There have been significant investments in fast chargers, and these fast chargers are strategically placed at these regular intervals along these major transport routes, so that this can allow for a quick recharging. And then there are subsidies for private charging stations. And then there is this public and private sector collaboration. So the government that is it has partnered with private companies in order to expand the charging network and offer incentives. And then another important factor is the public awareness, promotion, and the culture. So the government, the media, and the educational campaign that are highlighting the benefits of electric vehicles, promotional materials so that the people are informed on the financial incentives, and then public events and demonstrations. And then there is this broad cultural embrace of sustainability. So there is this pretty high level of environmental awareness in the Norwegian culture. And last but not least, we have research and education. So in Norway, there was quite a strong support in terms of grants for research, also in the field of electric vehicles technology. There are collaborative projects between universities and research institutions and industry. And I was actually part of one of them, and we will talk about it later in the presentation. And then, of course, Norway offers educational programs that include renewable energy, sustainability, and this, of course, indirectly tackles also the green transportation. And then public and private sector initiatives facilitate knowledge sharing and dissemination. So when it comes to research and education, as we said, let's have a look at one specific subject, that is informatics. So what is the role of informatics in these electric vehicles adoption? Which are the popular fields of application, and what is the state of the art? So one very popular field of application is the use of computer science for battery management system. So this means developing tools for real-time monitoring of battery health, battery charge and discharge, and also continuous data collection and real-time processing of data. Then we have quite a lot of research that is done in the field of predictive analytics for extending the battery life, and also prescriptive analytics in order to optimize the performance. And then the development and the use of computer models to simulate battery behavior under different conditions. And then another flourishing field of research in informatics is smart charging infrastructure. And here we see researchers developing models and algorithms for optimal scheduling and optimal management of charging sections. Then we have tools for load balancing, dynamic pricing models. We will talk a little bit about it later because this was part of one of the projects that I worked with. Then we have the integration of renewable energy, and then models for charging site expansion and management. And with this last point also, we will spend a few more words later. Then another very important field of application of informatics is vehicle-to-grid technology. So vehicle-to-grid are systems for this bidirectional energy flow between the electric vehicles and the power grid. So this means that the electric vehicles can not only draw power from the grid, charge the battery, but they can also send the electricity back to the grid when this is needed. So then computer science comes in the picture for the development of real-time communication protocols between vehicles and the grid operators. And then for the development of algorithms for optimizing energy storage and the operations of charge and discharge. And these algorithms then are very useful because they can help balancing the supply and demand. They can improve the energy resilience. They support renewable energy integration, and broadly speaking, they allow for cost saving. Another quite important field of application is route planning and navigation. And in this case, we have, for instance, advanced navigation systems that are tailored for some specific needs of electric vehicles. For instance, the need to take into account the degradation issues, the need to consider the location of charging sites so that the electric vehicles can charge at the right time. And then there's a lot of development in machine learning algorithms to predict optimal routes, again, based on the battery levels, on the driver's habits, on the different objectives of the prolonging battery lifetime, and so on. And then we have route planning that can be made energy efficient so that we can maximize the range, and the broad integration with smart grids, which is optimal charging times based on electricity prices. Another interesting field that is gaining more and more attention is autonomous driving systems. And here we see the connection between artificial intelligence, machine learning, computer vision, real-time data processing, so that we can enable vehicles to navigate and operate without the intervention of humans. And then under this umbrella, we see people developing decision-making softwares for navigating the complex driving scenarios, and then simulations and the testing platforms for validation. And another very important field to mention is, of course, cybersecurity, because here we see data encryption to ensure secure communication between the electric vehicles and the grid, authentication mechanism, threat detection, and then, broadly speaking, secure software development for the vehicle-to-grid technology. And under this very broad umbrella of computer science, then there is one subject in particular that plays a key role And this is mathematical modeling and optimization. So let's briefly look into what it is, why it is useful, and what can we do with it. So mathematical optimization is a method that is used to find the best possible solution to a problem within a defined set of constraints. And it has an important role because it helps making the best possible decision by taking into account many different options and then choosing the one that achieves a desired goal within a certain set of constraints. And it plays a very important role also in the electric vehicles sector. It's been used in many different sectors, but we see that it is increasingly used also within the green transportation and electric vehicles sector. So let's just have a broad look at the possible applications of mathematical optimization. So we see, for instance, optimal load balancing, so that we can optimally manage the timing of EV charging. Then we have optimal integration of renewable energy, optimal placement and the capacity planning, and then, of course, optimization of vehicle to grid, so that we can get to know when the electric vehicles should supply energy back to the grid, and how should we optimally manage the system to stabilize the supply and the demand. And then other fields of application that we see a lot in research, route optimization, so that we can find the optimal, most efficient routes, so that we minimize the travel time or we minimize the energy consumption. Then we see minimization of costs, and this is development of models that aims at minimizing the costs for infrastructure development, but also the operational costs of charging. And then we see scheduling of public transport, emission reduction, and then these models, they become tools, they basically become decision support system tools that can be used for scenario analysis. So this means that we can use these models, and then we can feed them with different data sets based on different scenarios that we want to analyze. And then we can run this so-called what-if analysis, so we can better understand what would happen, what would be the optimal decision if a certain scenario or another scenario is happening. And this scenario analysis is then what provides insights for policymakers, so that they can make more informed and effective decisions. So now I would like to briefly go through a few relevant past research projects where I've been involved while I was working in Norway, both as a postdoc and as a researcher. And they were all involving mathematical modeling and optimization. So the first one was this project. It was called Charge Reflex. The objective was to investigate alternatives to costly grid reinforcements to face the increasing demand of electric vehicles charging. And under this project, we worked on two main sub-projects that resulted in two different models. One was a stochastic multi-horizon approach for charging sites management, operations, design, and expansion. And the other one was related to indirect control of electric vehicles charging, and this was done through price signals. So for the charging site expansion project, this project started with these broad assumptions and motivations, that we knew that the investment costs of battery storage and renewable sources was supposed to drop in the future years and due to the technological improvements. But at the same time, we also knew that there was a forecasted increment in demand and electricity price. And of course, you can see an example of different trends that were generated for these battery costs, renewable costs, demand and electricity price. You see that we use different scenarios over 10 years time horizon. And these scenarios, of course, they were developed at a qualitative level because, when you work with such long-term models, then you need to create scenarios based on qualitative analysis, discussions with experts, results that you can find in reports of energy agencies and so on. So then we knew that there could be different long-term scenarios. And then we developed an optimization model, which is this decision support system tool, in order to analyze the grid reinforcement decisions in terms of a transformer and the power lines, and also how to spread out investments in battery and renewable energy sources throughout the years in order to mitigate the costs of grid reinforcements that were needed today. So we developed a multi-horizon mathematical optimization model. Multi-horizon means that inside the model, we are taking into account both the short-term and the long-term uncertainty. And the long-term uncertainty is given by the different scenarios, long-term scenarios that we talked about in the previous slide. And then inside the model, we also have a very detailed representation of battery degradation and decisions in terms of replacement throughout the years. And we also take decisions in terms of transformers and cables upgrade throughout the years. Here you see just an example of how a result might look like. So you see in this figure here that based on different scenarios of increasing demand, then the model can tell when to invest in batteries, and so when the replacements are happening and how much we should invest in it. And based on these battery investments, then you see different colors that correspond to the different grid reinforcements that are proposed for different scenarios. And then in the other figures, you see that the model has also the possibility to choose between batteries of different types. So depending on the different scenarios, then it was possible also to see how the model was installing a more costly battery, but that could last longer as compared to a cheaper batteries that would degrade faster. And this work is published in Journal of Energy Storage. So if you want to read more about the model development, the equations, and the extensive analysis, then you can find it online. The other project under this ChargeFlex initiative was indirect control of electric vehicles charging. And the objective here was to develop optimization models for electricity price signals and demand response of electric vehicles. So the key aspect of this model was the integration of this microeconomic concept of elasticity inside the optimization framework. So what is elasticity? Elasticity is this microeconomic concept that is used to measure the change in the aggregated quantity demanded of a service, in this case, charging requests, in relation to changes in the prices of that service. And in this model, we included two types of elasticity. We have self-elasticity, which means the percentage variation of demand in a certain time step due to a percentage variation of the price in the same time step. And then the cross-elasticity, which is the percentage variation of the demand in a certain time step due to the variation of the price in another time step. So the idea was to develop this model that was taking into account the drivers' elasticity matrices in order to develop an optimal list of price signals so that it was possible to influence the drivers' behaviors so that we could discourage a portion of drivers from charging when there were capacity limits issues, but we were still getting an optimized price signal so that still a portion of drivers will charge at the highest price. And you can see in this figure, this is a very simple example of the concept. So you see that we have here an elasticity matrix, which contains both cross-elasticity and self-elasticity. And here you see that we start from a reference price, so the initial price. And then here you can see that there is a certain demand and a capacity limit. So when we know that the demand is exceeding the capacity, then based on the forecast elasticity values, we are able to define a new price that is higher than the reference price, but it is higher such that only a portion of drivers will be discouraged and then charge in another time step, but still most of them will charge during that time step. So this was the broad concept of this project. And again, we have a publication. So you can read more about the model and the elasticity and how the model is designed. And you can see extensive sensitivity analysis that explain how the concept works. Then another project that is okay, then I will try to go fast. So this is another project that was kind of related to the electric vehicles sector and the increasing demand. This is the development of techno-economic optimization tools to study again how the power systems expansion decision can be taken in a more economical way, minimizing the costs of network reinforcement and reconfiguration. So again, it was a multi-horizon model where we included maintenance cost of existing power lines, technological learning coefficients, long-term horizon. And this can be applied, it is a broad model that can be applied to many different problems where we have issues of increasing demand, but it has good applications for the case of electric vehicles. And here you can read more about the paper that was developed. Then we also had the master thesis, optimal sizing and placement of electric vehicles charging stations to serve battery electric trucks. Maybe since there is not much time, then I will skip it. You can find the thesis, the master thesis, online on the UIT web page. So what is the future of green transport, which are emerging trends, and what is Norway's vision? Here we have a list of trends, which is, what the research is mostly doing now, and what is going to be the focus in the forthcoming years. We have vehicle to everything technology, swarm intelligence for electric vehicle fleets, further charging infrastructure expansion. Now there is this dynamic wireless charging systems, leveraging 5 giga to enhance vehicle connectivity, the use of edge computing, environmental sensors and digital twins for electric vehicles infrastructures, and then the urban mobility as a service, shared mobility, and the use of AI to learn individual driving patterns and then optimize the energy usage, and also algorithms to adopt that can help the drivers adopting more eco-friendly driving habits. So where is Norway going now? So they have this objective of zero emission new car sales by 2025. And this also applies to zero emission heavy vans, long distance buses and lorries by 2030. So that the benefits of electrification can go beyond the passenger vehicles to other segments of the transport sector. Then Norway aims to significantly enhance public transport systems, further development of charging infrastructure, focus also on green shipping and also green sustainable aviation. There is this Oslo zero emission goal, this plan that the city has to become the world's first emission-free city by 2030. And then, most importantly, adjust economic incentives. We saw in the initial slide that the market is kind of approaching maturity. So what is happening now is that the incentives are being adjusted or lowered. For instance, they are introducing this 25% VAT on the portion of an electric vehicle's price that exceeds a certain amount. There is a weight-based tax. And this is done to encourage market maturity so that they can also redirect resources to other areas. And then, last but not least, still a lot of investment in research and development. There are still projects going on regarding green transportation and sustainable batteries, as you can see here. But there are also many others. And then the new energy informatics-based courses and study programs that are being discussed, project proposals, focusing on educational aspects with emphasis on sustainability. So to conclude, Norway's vision emphasizes this holistic approach. We've seen that there is this combination of government support, technological innovation, public engagement, and it is very important to focus on research and especially interdisciplinary collaboration to advance the transportation field and to enhance these green technologies. And then if we integrate different fields of expertise, including, of course, computer science and energy informatics, we can develop sustainable infrastructures and solutions so that we can support both environmental and economical goals. Thank you.
So regarding the user adoption of vehicle to vehicle or vehicle to X sort of technologies, do you believe that there's a large enough user adoption, like organically, to make it an actual thing that we can account on, or do you think it needs some kind of help?
Well, I think yes, it needs anyway some kind of help, as we were discussing at the beginning of the presentation anyway. Information and the sharing, information about the benefits and so on, then this is important. So it's not something that can happen alone, but there is a need for, this holistic approach, government policies, research, industries, and so on. Yeah.
Maybe a follow-up question. So, since you are a bit further with the adoption of EVs in general, from your modeling, do you have any idea about this vehicle to grid or vehicle to X, the possibilities? How much will they contribute to the green transition in Norway at all? Is it more cream on top of the cake, or is it really something that we need, that is essential for becoming climate neutral?
Yeah, I think this is a very good question. I don't have insights because I didn't work on vehicle to grid modeling, but I think this is a very good topic for a research project, definitely. So, yeah. More questions? Yes.
So I'm quite curious about what you told about this price signal, where only a certain share reacted to the price. Because in Denmark, especially after the Ukraine and Russian war, Danish EV owners are really looking into when the price is cheapest. So they adopt these solutions where it charges in the cheapest hours. So in Denmark, I wouldn't expect that to work because it would automatically just move everyone's charge to later.
Well, the key of that model was the inclusion of this elasticity concept. So the elasticity is very much related to how the perception of the driver. So it is not necessarily true that a person would always choose to charge when the price is lower, because you might find yourself in a situation in which you really needed the charging. I mean, you might not be happy to pay that price, but you might not have any other option. So depending on the type of situation that you are finding yourself in. So this is why the concept of elasticity is important. So understanding in different times of the day what is the sensitivity of the drivers to different prices. So it's not straightforward that you will always charge at the lowest price, because sometimes you might not have options.
Very nice. So in this part that is regarding the restructuring of the grid, so is it a theoretical conference or you have used some actual grid?
We use we use some real world data. But then in the paper that you see, in order also to validate the model and show how the model works and what is the value of the model, we also used, created some additional scenarios with fictitious data. But the scenarios that you see, the qualitative level, they were developed using real discussions with industries and readings of reports and so on.
Because here in Denmark, we don't have so many, automatic switches for this structure. So that's why I asked this. So therefore, you have.
I thought you were asking if I was using real world data for the analysis. Yeah.
But if you have used the real world system, so your assumption is that you have automatic switches. But my point is that here we don't have. So probably you have it. Yeah. That was a comment.
Okay. Thank you. Good.